Why is it that you can never see the universe as it truly is? The answer is the speed of light limit. But have you ever wondered why there is an upper limit to the speed of light? What would happen if the speed of light were just 1 meter faster or 1 meter slower? In the next 30 minutes, we are going to delve into the secrets of the universe, their speed limit. We also hope this video will give you an enjoyable journey at the speed of light. To understand the universe's speed limit, we need to break it down step by step. First, let us talk about the speed of light. Simply saying 299,792,458 meters per second might not mean much to you. Let us look at it from another angle. First, let us take a look at humanity's journey to push the limits of speed. For thousands of years, the speed limit for humans was set by our own legs. The fastest messengers could cover 100 miles a day. Converted, that is only a few meters per second. Later, we learned how to ride horses. Our speed increased to over 10 meters per second. This small improvement, it invisibly brought the empire's borders closer, until the roar of the steam engine was heard. Human speed reached 10 meters per second, and today, the British designed and manufactured supersonic car thrusts can reach 341 meters per second. But cars are not the end of speed. When we turn our gaze to space, the Parker Solar Probe has broken the human speed record, reaching 192 kilometers per second. However, all of this is almost motionless compared to the speed of light at 300,000 kilometers per second. It is so slow, it is nearly at a standstill. Do you have a better sense of just how fast that is? Of course. Besides its speed, light it is also a tiny data packet. You could say it is a tiny messenger of the universe. But the strange thing is, it has no rest mass, and it never stays still. What is even more interesting is, light is both a particle and a wave. Not a wave like those in the ocean, it is an electromagnetic wave, a vibration of electric and magnetic fields. These two fields oscillate perpendicular to each other, and also perpendicular to the direction of propagation. And these waves do not require a medium to travel. This is crucial. Most waves, like sound waves and water waves, or even the wave your arm makes when you wave to your neighbor over a fence, all need something to act as a carrier. Sound needs air, water waves need water. But light just travels like that. It can pass through the vacuum of space without any obstacles. Because of this, we are able to see the sun, which is about 150 million kilometers away. Its rays travel across the endless void and reach us after 8 minutes. And the light we can see is also called visible light. It is just a tiny part of the entire electromagnetic spectrum. Imagine a piano stretching for several kilometers. Visible light is just a few keys in the middle. At one end of the spectrum are radio waves, which can be several kilometers long. At the other end are gamma rays, which are sharp, high-energy pulses that can penetrate almost any material, usually occur alongside stellar explosions and nuclear reactions. Between these two, there are also microwaves, the infrared used by your TV remote control, the ultraviolet rays that give you sunburn, and the kind that can see through your bones, but not your clothes. X-rays. Yet, despite all these differences, all these forms of light, their speed of propagation in a vacuum is always the same. About 300,000 kilometers per second, a number so large it feels unreal. But light does not always travel that fast. When it passes through water, glass, or even diamond, it slows down. Because it is interacting with the atoms in the material, it is a bit like moving through a crowded crowd. Even though you are moving in the same direction, you still need to constantly collide and adjust your path. This slowing down causes refraction. It is the bending that happens when light enters a different medium. That is why a straw in a glass of water looks bent when you see it, or why diamonds can sparkle so brilliantly. It all comes down to how the journey of light is delayed, detours and scattering. But what is fascinating is, even though light slows down in these mediums, a single photon, in the gaps between atoms, still travels at that ultimate speed. It is just taking a more complicated path. When we talk about color like rainbows, prisms, or that strange oil film in a puddle, what we see is light being separated into different wavelengths. Each color in visible light has a different wavelength. Red is the longest, and violet is the shortest. But they are all photons. They are all electromagnetic waves, just vibrating at different frequencies. You have special cells in your eyes called cone cells. They are sensitive to specific ranges of wavelengths. That is how you see color. It is not that the apple itself is red. Rather, it reflects wavelengths that our brains interpret as red. At the same time, it absorbs the other wavelengths. In a sense, color is simply your brain's best guess based on which vibrations reach your retina. Here's the most amazing part. Light has no rest mass. That means it does not need energy to move. Instead, it is always moving. It has no choice. If a photon stops, it ceases to exist. It either moves or it disappears. That is physics. We have these massless packets of energy, which behave both like waves and particles, traveling at a universal speed. It can interact with atoms. It can bend around corners and bounce off surfaces. At the same time, it brings our brains the experience of vision and color. Light is an eternal traveler that never stops. It is made of pure energy, not matter. At the same time, it follows the strangest rule in the universe. One it can never break, and a speed that will never fall behind. And this is just scratching the surface. In fact, for most of human history, people believed that light traveled instantaneously. It was simply there. You light a candle, and the room is bright immediately. The sun rises, and the world lights up. No waiting. No delay. It was not until the arrival of Galileo that everything changed. Around 1638, he attempted to measure the speed of light. At the time, this was considered one of the most seemingly ridiculous experiments. He used the simplest method. Galileo and his assistant each held a lantern with a cover. They stood on hilltops about 1.6 kilometers apart. Galileo would uncover his lantern. As soon as his assistant saw the light, would immediately uncover his own lantern in response. Galileo then measured the time between sending the signal and seeing the returning flash. Now we know that this kind of experiment simply can't measure the speed of light. A human's reaction time is about 1/4 of a second, but it takes light less than 1/10,000th of a second to travel a kilometer. It is like trying to measure the speed of a bullet with a sundial. Nevertheless, Galileo unsurprisingly concluded, if light does have a finite speed, it is so fast that he could not measure it. That is true, but at least the question had been raised. Decades later, a Danish astronomer named Romer, in 1676, by observing a rather distant celestial body, one of Jupiter's moons, he unexpectedly found the answer. Romer was tracking the orbit of O, one of Jupiter's many moons. It raced around the giant like a cosmic clockwork mechanism. By carefully observing when O disappeared behind Jupiter, and when it reappeared, he noticed something strange. The timing was not always consistent. Sometimes O appears a bit later, and sometimes a bit earlier. At first glance, this seems like an observational error, but Romer came up with a brilliant idea. What if it was not O that was being inconsistent, but us? What if the delay was because Earth is sometimes farther from Jupiter, and the light from O has to travel a longer distance to reach us? So, the idea of measuring the speed of light began to take on a truly scientific form. Based on these differences in timing, Romer estimated that light takes about 22 minutes to cross the diameter of Earth's orbit. We now know that this distance is about 300 million kilometers. Considering he had no precise distance data or modern clocks at the time, his result was already quite impressive. His estimate was not perfect, but it was revolutionary. It tells the world, light needs time. Not much, but enough to make a difference. Later, in the early 19th century, a physicist named Hippolyte Fizeau decided to try a more down-to-earth approach. His method involved a beam of light, a spinning cogwheel, and a mirror placed several miles away. Here's how it worked. A beam of light passes through the gap in the gear, travels to a distant mirror, and then bounces back. If the gear turns slowly, the returning light will pass through the same gap. It can be seen, but if the gear spins quickly, the returning light will hit the tooth instead of the gap, and will be blocked. By adjusting the speed of the gear, Fizeau could find the exact point where the light beam was completely blocked. This meant that light had just enough time to travel to the mirror and back, while the gear rotated by half the width of a tooth. Using the known distance and the speed of the gear, he calculated the speed of light to be about 310,000 kilometers per second. That is not far off from the modern value, especially considering he was using mirrors, gears, and a great deal of ingenuity. Later on, another scientist, Learn Foucault. Improve this technique by replacing the gears with a rotating mirror, greatly increasing the accuracy. He not only proved that light travels at a finite speed, but also that light travels slower in water than in air. This was a crucial clue. It shows that the interaction between light and matter can affect its speed. But among all these names, perhaps the most iconic is Albert Michelson. At the end of the 19th century, Michelson adopted Foucault's method and refined it to an unprecedented level of precision. He used long tunnels, meticulously calibrated mirrors, and extremely precise timing. He arrived at results that shocked the scientific community. His efforts earned him the Nobel Prize in Physics in 1907. He became the first American to receive this honor. For someone who chased beams of light with mirrors, that is quite a reward. Today, we have better tools: lasers, atomic clocks, and satellites. We even define the meter based on the speed of light itself. Since 1983, the meter has been officially defined as the distance light travels in 1 per 299,792,458 of a second. In other words, we have flipped the equation. We no longer measure the speed of light, but instead use it as the standard to measure everything else. Having learned about the history of the search for the photon, let us dive into the real question that truly puzzles physicists. Why can't light go any faster? After all, it seems like a rather arbitrary number. Why is it 299,792,458 meters per second? Why is not it a nice round number, like 300 million or 500 million, or even just infinite? Why is it that light, this elusive, massless beam of energy, do we really have to obey the speed limit of the universe? To understand this, we need to step into one of the most perplexing fields in physics. Electromagnetism. More specifically, we need to talk about a man named James Clerk Maxwell. In the 1860s, Maxwell took everything scientists knew at the time about electricity and magnetism. They were consolidated into 4 mathematical equations. These equations are known as Maxwell's equations. They describe how electric and magnetic fields interact, change, and move. Do not worry. We are not going to discuss these equations. Maxwell combined these equations. He discovered something extraordinary. They predicted the existence of a kind of wave, a type of electromagnetic wave. As long as the electric and magnetic fields oscillate in the right way, it will naturally be generated, and this wave will always travel at a specific speed. When he did the calculations and plugged in the known values for the electric and magnetic constants, he got a number that is right. It is the number you are thinking of, about 300,000 kilometers per second. Maxwell was stunned. He had discovered a fundamental speed in the laws of electromagnetism, and the key was, this number matched exactly with the best measurement of the speed of light at the time. This was not just a coincidence, it was a revelation. Maxwell realized that light, it is a kind of electromagnetic wave. It is a ripple of electric and magnetic energy propagating itself at a speed determined by the very structure of the universe itself. It races through the void. The speed of light is built into the equations that govern the structure of reality. It is not a random setting of the universe. Rather, it is the way the universe has to work. If electric and magnetic fields exist, then light must travel at this speed. That is part of the answer. The reason light moves at this speed is because it is an electromagnetic wave, and this is the only rate it can propagate in a vacuum. Any faster or slower rate would break the laws of physics as we understand them. To find out why the speed of light is constant, let us invite our next physics genius, Albert Einstein. 1905, Einstein published the theory of special relativity. A key assumption of special relativity is the speed of light in a vacuum is the same for all observers, no matter how fast they are moving. Do you know how mind-blowing this theory is? Just imagine, you are on a train traveling at 90% the speed of light. You turn on a flashlight. Common sense tells us the speed of the flashlight's beam plus the speed of the train should be much greater than the speed of light. So for someone standing on the platform, the light from your flashlight would appear to move faster. But the result is counterintuitive. Both you and the person on the platform measure the speed of that beam of light to be exactly the same, still 299,792,458 meters per second. To make this possible, Reality has to bend itself around this rule. Time slows down. Lengths contract, and mass increases. The universe changed the way it operates, to ensure that no one, no matter how fast they move, observe light speeding up or slowing down. And there is another rule that is just as inescapable. Suppose you are an astronaut trying to accelerate your spaceship to the speed of light. You will run into a problem. As your speed increases, your mass is also increasing, but it means you need more and more energy, just to go a little bit faster. As you approach the speed of light, your mass tends toward infinity. This means you would need infinite energy to reach the speed of light. Infinite energy is simply impossible in reality. No matter how hard you try, you can get close, but you can never reach it. In other words, you can never catch up with light. It is why the speed of light is more than just the speed of light. It is the ultimate speed limit of the universe. It is the maximum speed at which information, energy, or anything with mass can travel through the universe. It is a barrier, a boundary, fundamental part of space and time itself. To put it more simply, if the speed of light had no limit, reality would fall apart, because causality would be broken. Just imagine, you could observe a result before its cause even happened. For example, you see a cup shatter, and only then see it fall off the table. Reality would be a complete mess. It is full of theories about time travel and serious logical consequences. On the contrary, the universe uses this speed limit to protect us from that kind of chaos. It keeps things orderly and predictable. No matter what else changes, the speed of light always stays the same. Now we know that if there were no speed limit for light, causality would become chaotic, but what if the speed of light became very slow? For example, what if it slowed down to just 100 kilometers per second? That would not be a more relaxed world. It would be a universe in which we simply could not survive. First of all, the energy source you rely on most, the sun, would go out. The reason the sun shines and gives off heat can be perfectly described by Einstein's famous equation, SE. It converts tiny amounts of mass, converted into tremendous energy. If the value of the speed of light became very small, then c squared would become even smaller. This means that each nuclear fusion would release only a tiny amount of energy. Our sun, this magnificent fusion reactor, would instantly become a dim, fading ember, and Earth would plunge into eternal freezing. Secondly, the bizarre effects of relativity will become part of your everyday life. You no longer need to ride a spaceship near the speed of light to experience time slowing down. Maybe you are just driving on the highway. Your watch would run much slower than the clock on the wall at home. When you look at the buildings flashing past the window, they would appear flattened to your eyes. The real world would become a distorted picture. Distorted, grotesque paintings. But the most terrifying thing is not even that. The speed of light is deeply rooted in the laws of electromagnetism. If the speed of light slows down, it means the electromagnetic force that governs atomic structure and chemical bonding would fundamentally change. The very rules that keep the material world stable would collapse. Atoms might not be able to hold onto their electrons stably. Molecules would fall apart. The matter that makes up your body, the table, the air, and even the entire planet could instantly lose its structure. You might think, this is an extreme scenario where the speed drops to 100 kilometers per second, but what if the speed of light were just 1 meter per second slower than it is now? The answer is, the nature of the disaster would be exactly the same, because the speed of light is not an isolated number. It is the glue that holds all the laws of the universe together. Even a seemingly insignificant difference of 1 meter can lead to 2 fatal consequences. First, the laws of electromagnetism that hold matter together would immediately fall apart. All the atoms that make up our world would instantly lose their grip on each other. Matter will cease to exist. Second, according to the mass-energy equation, all matter in the universe would have to adapt to this new speed of light and would instantly release an enormous amount of energy. Simply put, the entire universe would, in an instant, turn into a cataclysmic explosion that engulfs everything. A universe with a slower speed of light, no matter how much slower, would be a universe where energy runs out of control, matter falls apart. Now you might truly understand why the speed of light is exactly what it is now. Not a bit more, not a bit less. It is not an option, but the only cornerstone for the universe to exist in a stable way. This might be the most merciful gift the universe has given us. The universe did not choose the path of falling apart. Instead, to preserve this sacred number, it chose a stranger way to bend itself. And this was exactly Einstein's greatest contribution. When he proposed his special theory of relativity, it was his most remarkable achievement. He did not just adjust the rules of physics. He rewrote them to better understand this intuitively. Imagine you are in a spaceship. You are holding a flashlight. You turn it on, and a beam of light shoots forward. Imagine another astronaut riding in another spaceship, flying past you at 50% the speed of light. From his perspective, you and your spaceship flash by like a blurry shadow. But when he measures the speed of the same beam of light, it is still exactly 219,792,458 meters per second. This completely defies our everyday understanding of the world. Speeds are additive. If you are walking on a moving walkway at the airport, your speed equals your walking speed plus the walkway's speed. But for light, the walkway can move, the person can move, the flashlight can move, yet the speed of light remains the same for all observers. How can that possibly be? Einstein's solution was, it is not the speed of light that changes, it is everything else. Time, space, the passage of moments, the size of objects, all of these things bend and stretch. To preserve that sacred number, first, time dilation. The faster you move, compared to someone at rest, the faster you move, the slower your time passes. This is not just a subjective feeling, it is a real, measurable effect. For example, imagine you are on a spaceship traveling at 90% the speed of light. For you, only a week would have passed when you returned to Earth. For everyone else, much more time would have passed, maybe even years. When you go on a brief journey, the Earth ages while you are away. This is not just a theory in books. We have already verified it. Cosmic rays in the upper atmosphere produce particles called muons. They decay within microseconds, but when they travel near the speed of light, their internal clocks slow down, so their lifespans are longer, long enough to reach the ground and be detected. When they move, time really stretches for them. Secondly, length contraction. This is the strange twin of time dilation. When you travel at high speed, objects in the direction you are moving will appear shorter. This is not an optical illusion, it is a physical reality. If you measure your spaceship along its direction of travel, it will actually become shorter before you imagine yourself being squashed into an uncomfortable cube. Keep in mind, this only becomes noticeable when you are close to the speed of light, but when it comes to everyday speeds, the effect is so small it can be ignored. But as you approach the speed of light, the universe becomes elastic. And then, there is the relativity of simultaneity. Simply put, for one person, two events may seem to happen at the same time, but for another person moving relative to them, they may not happen at the same time. Imagine a fast-moving train. A light bulb flashes right in the middle of the train. From the passenger's perspective, the light reaches both the front and the back of the train at the same time, but for someone standing on the platform, the light reaches the back of the train first, because the front of the train is moving away from the flashpoint. Both observations are correct. Time and space are no longer universal. They are flexible, local and relative. All these strange phenomena, time dilation, length contraction, the breakdown of simultaneity, all happen to preserve that constant speed of light. It is if it is the universe's contract. In order to keep the speed of light constant, the universe agrees to distort everything around it. It is an exquisite balance that maintains the integrity of causality. This is exactly where Einstein's work is most brilliant. He not only described the speed of light as a limit, he also showed that it is the cornerstone of the universe. It is the cosmic framework that supports time and space. So far, we have explored light itself, what it is, how we measure its speed, why its speed is such a precise and unbreakable limit. But now, let us gently pull back the lens and see what this universal speed limit actually does to reality. To do that, we need to start with another key to understanding the universe: time. The speed of light limit gives time a certain structure. It tells the universe you can only connect 2 points if light has enough time to travel between them. Only then can they be linked. This is what physicists call the light cone. Imagine you are standing in a field, and you light a match. The tiny spark sends light out in all directions. The farthest distance that can be affected by that matchstick, whether immediately or eventually, is limited by how far light can travel from that moment on. If someone is standing very, very far away, 100 light years away, they would not know the match had been struck until 100 years later. Let us think about it the other way around. Imagine you are standing in the same field, waiting for something to happen. The only events that can affect you at this moment are those whose light has had time to reach you. This is your past light cone, all the events that could have led to your current moment. A light cone is not just a clever diagram. It is the boundary between what is possible and what is impossible. If something happens outside your light cone, it is just too far away in time. Any signal from that event still can't reach you here. It is as if it does not exist at all, not until the light arrives. This idea has shaped our entire understanding of the universe. It means there is no such thing as a true now. Instead, every moment is local. Every now is slightly different depending on where you are. And the speed of light is the rulebook that keeps all of this consistent. When you look up at the light from the nearest star system, it takes more than 4 years to reach us. If something dramatic happened there last week, it would still be years before we found out. And that is just our neighbor. Look farther, and the effect becomes even more pronounced. Light from the Andromeda Galaxy takes over 2 million years to reach us. What you see is how it looked when early humans were just learning to make tools. Go even farther out, and we see light that left its galaxy billions of years ago, when our sun did not even exist yet. And yet, it all feels so real. The stars twinkling, the galaxies glowing, they seem to be right there. But actually, they are not. That is a history written with beams of light. It moves forward at its own pace. This delay makes astronomers, in a sense, time travelers. When they venture deep into space, they are not just looking into the distance, they are also looking back into the past. Every telescope is actually a time machine, peers into long-lost history. And all of this is because light does not travel instantaneously. Its limitations mean we can only see the past. Is there anything faster than light? After all, humans have always had a habit of challenging limits, so let us take a look at quantum entanglement. It is one of the most bizarre phenomena in all of physics. When two particles become entangled, measuring one seems to instantly affect the other. No matter how far apart they are, they react in perfect sync. Although this action at a distance is faster than light, it can't be used to transmit usable information, because you can't control the measurement result of a particle. You can't use it to send messages. It is like two people tossing identical coins across the universe and always getting the same result. But neither can use it to say hello to the other. Einstein himself was deeply troubled by this. He called it spooky action at a distance. But modern experiments have confirmed that entanglement is real, and it does not allow for faster-than-light communication. The universe is strange, but it still respects the speed limit. Next is Cherenkov radiation, a bizarre phenomenon that glows. When a charged particle moves through a medium like water at a speed faster than light travels in that medium, it happens. Yes, you heard that right. Light in glass, or materials like water or plastic, does not always travel at its full speed. Because of interactions with atoms, it moves a bit slower. If a particle moves faster than that reduced speed, it creates an optical shock wave, similar to a sonic boom. That is what you see in a nuclear reactor immersed in water. The reason we see the strange blue glow is not because something has broken the universal speed limit. It is just that the local speed limit within the material has been exceeded. Light in a vacuum is still the supreme ruler. No real law has been broken. It has just been slightly bent in the pool. As for warp drives, although in theory, maybe it could, but it would require some extremely unusual materials. For example, exotic matter with negative energy density. We are not even sure if such things can actually exist. Warp drives still remain in the realm of imagination. Of course, there is also the idea of wormholes. Even if you could make a wormhole work, Technically, it is not faster than light travel either. You are just taking a shorter path. Despite all sorts of clever ideas and strange exceptions, no object with mass or information has ever been observed traveling faster than light. Whenever we think we have found a loophole, the universe closes it up. The speed of light is like a door locked at the edge of possibility, but in reality, it is more like a safety rail to prevent the universe from falling into solipsism and chaos. It gives us structure and order you may have already sensed. The speed of light is the cornerstone of the universe, but what if it is even more profound than we realize? Let us take one step further together. In modern physics, the role of the speed of light is far more than just the speed of photons. It is more like a built-in conversion rate of the universe. You must have seen it in Einstein's famous equation. SE. Here, the square of the speed of light is the magnificent bridge connecting mass and energy. It tells us that even in the tiniest bit of matter, an enormous amount of energy is locked away. Its real magic lies in the fact that it is also the bridge connecting space and time. Think about it. We use light year, a term measured in years, to measure distances in the universe. This unit we take for granted already implies that time and space are deeply intertwined. This idea leads to a truly fascinating conclusion. From the perspective of a photon, it does not experience time the moment it is emitted and the moment it is absorbed. Happen simultaneously for anything moving at the speed of light. Time stands still. This forces us to rethink. Maybe the universe was not built to let light move. On the contrary, the entire structure of the universe, it was built around the constant and unchanging relationship of the speed of light. And these profound laws of the universe are not only found in distant galaxies or on physicists' blackboards. They are silently, almost imperceptibly, quietly, woven into the fabric of our daily lives. The most classic example is the GPS navigation you probably use every day. For precise positioning, your phone needs to receive signals from multiple satellites. But because these satellites move at high speeds, their own time runs a bit slower. Since they are in high altitudes with weaker gravity, time actually runs a bit faster for them. The GPS system must rely on the constancy of the speed of light, while also making nanosecond-level corrections for both of these relativistic effects. Otherwise, your GPS would take you several kilometers off course every day. Einstein's theory is helping you find your way home. Similarly, from the fiber optic cables that form the backbone of the internet and allow you to watch this video, to the starting point of energy for almost all life on Earth, photosynthesis, from the microwave that warms your food to the Wi-Fi signals connecting you to the world. We watch, communicate, navigate, and survive, all unconsciously following the laws of light. It is the engine that quietly and reliably drives modern life. What light connects goes far beyond this. It has not only shaped our present, it also brought us the oldest echoes from the dawn of the universe, the very oldest echoes. That is the cosmic microwave background radiation SEMEM. It is not light from any star or galaxy. Instead, it comes from about 380,000 years after the Big Bang, when the universe finally turned transparent from a chaotic, dense fog. These were the first photons able to travel freely. They have journeyed undisturbed for nearly 14 billion years. Today, it still gently bathes everything in the universe, including us, when we detect it. What we see is the very first snapshot from the universe's childhood. It is archaeological evidence on a cosmic scale. By listening to this ancient light, and the light from distant stars, we have learned the language of the universe. We can read the chemical composition of galaxies. We can witness the birth of stars. We can even trace back every carbon atom in your body to the ancient stellar furnaces that forged iron and calcium. This is not just poetic. It is a scientific fact. We are all made of stardust, lives connected by the story of light. And so, gently, we return to where it all began. We set out to answer two simple questions. Why does light have a speed limit? What happens when the speed of light changes? The final answer is both elegant and profound. Light moves the way it does, because the universe is built to make it so, and is shaped by it. Its speed is not just fast, it is fundamental. From now on, whenever you look up at the starry sky, what you see will no longer be just a shimmering tranquility. Instead, It is countless photon messengers, crossing 10,000 years of time, bring you an epic of the universe. When you pick up your phone and connect to the internet, what you feel is no longer just the convenience of technology. Instead, it is the speed of light, the cosmic ruler quietly at work at your fingertips. We live in a world gently yet firmly shaped by the laws of the speed of light. Perhaps that is a good thing. The speed of light gives us order, gives us time, and gives us a way to understand. It gives us stories and sunsets, and the warmth of starlight on a cold night. Maybe we do not need it to be any faster. Maybe it is already perfect, just as it is. As we bring this tranquil journey to a close, allow me to ask once more, when this beam of light, carrying the secrets of light speed, travels through cables and signals, by the time it finally reaches your screen, what does the night sky look like where you are? Wherever you may be, rest well. May you see, in your dreams tonight, those stars traveling at the speed of light. Good night.